Okay, so let's get started. So I just wanted to let you know that we are working hard on getting lab 2 graded, but the TAs are spending a lot of time looking at each submission, so it's taken them much longer than I had anticipated. They hope to get it done this week, but I'm not so sure that it will actually get done before the lab 3 is due. So please bear with us. We'll still try to give you good feedback and whatnot. Okay. If you have any questions about anything, you should always come and ask, so that you have the best inputs from us to do a good lab. Okay. So beyond that, just a couple reminders. So we are almost done with the semester. Three more lectures after today, and we have a final exam next Friday. Yes, a take-home file. I did mean a take-home file. Yes, the semester is almost, not this week. I meant a week from my next time, and there's only 3 more classes left, and then we have an exam, and then we'll be done. But there's going to be a sprint to the finish, so bear with me a little bit. All right. Yes, please.
So what will be the format of the final exam?
Okay, what will be the format? So, okay, let me explain how the final exam will work. So we will hand out electronically the exam, maybe on Moodle or somewhere. We'll give you a PDF, okay, and then you will have 24 hours. It's a take home, meaning you can use whatever. You cannot discuss it with anyone other than me. Okay, you can ask me questions, but you cannot discuss it with anyone. You can use whatever material you want, anything on the internet, papers, any class notes. So there's no restriction. Whatever you use, please cite. Okay, it's important that you cite, because we will need to know what material you used. If you use class notes, you don't have to cite it. I mean any external material. Okay, please cite it. Typeset your answers. You are free to handwrite your answers, but then you have to scan it and you're going to turn in a PDF. Okay, so you'll upload that back to Gradescope or Moodle, one of those two. Okay, I don't know if that answers the question about format. Okay.
Will it be questions like the midterm?
Oh. Format is what kind of question? Okay, the questions will naturally be more difficult than the midterm, because that was a closed book, closed note, 90 minutes exam. This is an open book, open everything, 24-hour exam. It shouldn't take you 24 hours to do it, but it will take you more time and it will require you to think a little more. We won't ask you something like define X, because that's not a question you expect on a take-home exam. Okay, you will have problems or synthesize ideas and come up with solutions. That's the kind of questions to expect. Okay, yes, please.
So will it open at like 12:01 a.m. on Friday?
Oh, no, it got 9 a.m. to 9 a.m. 9 a.m. on Friday, due the following day. Okay, 24 hours. All right. Okay, so let's talk about distributed file systems. So today we start a new topic. So on today and on Wednesday, we are going to just spend 2 classes talking about file systems, storage, large-scale storage systems, and so on. Today will be more of an introduction. We'll only talk about file systems and NFS. Next time, we'll talk about a whole slew of other storage systems, including RAID and large-scale storage systems like Google file systems and things of that sort. Okay, so let's start a little slowly. We'll start with some file systems basics. This is next 2 slides are really undergrad material, just as a recap. Okay, so what's a file? A file is a named collection of logically related data. It's an abstraction that the OS provides you, so that's easy for you to actually create data objects, store them on disk, retrieve them, and so on. Okay, essentially it provides a logical view of the data. You don't actually need to understand anything about the physical nature of the disk, where your data is stored on disk and so on. You just need to know the name of the file, maybe the directory where it's stored, and the file system will take care of figuring out where it actually is stored on disk, how to get it to you, and so on. So it provides a much easier interface for humans to deal with data that they create. So you can create, modify, delete your data. You can share your files with other users. You can get protection by using protection features of the file system and so on. Okay. Now, there are many kinds of file systems out there, and they have different philosophies in terms of how they treat files themselves. Okay. The simplest one is the Unix file system, or there are many variants that you see today in Linux. You have things like ext2, ext3, ext4, and many other file systems. But by and large, what they assume is that a file is essentially a linear array of bytes. You do not actually interpret what is inside a file. You do not provide any interpretation. So the file is essentially an opaque array of bytes, so you don't attach any semantics to whatever is inside a file. There are many other file systems where files will have types. Okay, you will say this is a file that is an image, this is a file that's a Word document or a PowerPoint file. The file system will actually keep that information, and it expects that the file actually has a structure that's appropriate for that file type. Okay. Unix file systems don't. They just assume that all files are just an array of bytes. It doesn't matter what type of file it is, whether it's text file, binary, it doesn't really matter. Okay. Then directory is essentially, from a file system's perspective, a special file that's essentially an index of all the files that are contained within that folder. Okay. So the directory file essentially is just going to be a list of files in that directory. It could be other directories also, and then some pointers to those objects. Okay, so you will see that typical directory entry will have a file name, it will have an inode number. Okay, inode is essentially some metadata for a file. It's called index node. This is how file systems will figure out where they have stored their data. For every file, okay, the object, there's also going to be some metadata. Okay, so metadata is data about the data. Next time we'll actually look at file systems where there are data servers and metadata servers. There are actually different machines that keep track of where the information is stored and the information itself. Okay. So as far as Unix file system is concerned, all the inodes are stored at a special location on disk, okay, which is called a super block. Okay, so there are special blocks called the super blocks where you store all the metadata, and then there are regular blocks that are data blocks where you will actually store the files themselves. Okay. So this is just something you want to keep in mind. Okay, so now I'll very quickly show you. This is not really a good way to show it. I should have put a picture here, but let me draw a picture. Okay, so typical metadata structures, such as an inode, will look like this. Okay, so there will be, so this is a structure of inode. There's some information here which could be the name of a file, the user, so you'll have some last modified times, and so on. Okay, it's all information about the file itself. It's not really the data, but metadata. Okay. And then there's an index structure, okay, which is why it's called an inode. This is a multi-level index. Okay, so you can think of this as having n entries. Let's say the first 12 entries are direct block pointers. So they actually point to blocks on a disk. So let's say that's the disk. So they will point to different blocks on the disk, saying this is block 1 is stored here. This will have the address of those blocks. Okay. So the 13th entry actually points to a block which will itself have, so it's a multi-level index. Okay. So the 13th entry will itself point to a disk block that will have another 1024 pointers. Okay. These are direct pointers. This requires 2 levels of indirection. You follow this pointer to get here, and then follow each of those pointers. They point to disk blocks. Okay. The 14th entry in the inode is actually double indirect, which means that there will be pointer to a disk block. Each of this will point to disk blocks, and each of those disk blocks will have 1024 entries. Okay. So this is called double indirect, 2 levels of indirection, okay, as a multi-level index. And you can have also a 15th entry, which will give you triple indirect, okay, meaning that entry will point to a disk block, each entry in that will point to another block, each entry will point to another block, and those will point to actual disks, actual blocks in the file. Okay, is that clear? Now, depending on the size of the file, you will probably have not all of these entries populated. As the file grows, you can create these entries as and when you need them. So typically for every file, you will actually allocate only the inode. And if the file grows beyond 12 blocks, will you then allocate a 13th block which will have these pointers. If the file grows beyond 12 plus 1024 blocks, then you will allocate a 14th entry which will point to a block. You will then allocate the first block of that entry and then keep growing the file that way. Okay, so as the file grows, you add more metadata blocks so that you can accommodate all the pointers to disk blocks of that file. Okay. So now look up to any byte or any block of that file just requires you to map which block it is. So if you say I want byte offset X, you basically then say what block is it. So if you say it's block J, you will essentially have to look up the jth entry in this multi-level index. Okay, the jth entry could be the direct pointers, they could be in the single indirect, double indirect, or triple indirect. So you just have to follow the pointers and then you get to your block. Okay, this is how your file system is going to dereference some block that you are trying to access in the file. Is that clear? Okay. So that's inode, but now we'll sort of move on from files, inodes to distributed file systems. Okay. In a distributed file system, the main difference is that your files are now stored on a machine that's different from the machine you are accessing them. So there's a file server which is storing all your files, and there are clients that are going to actually access those files over a network. Okay. If you use Windows and created network drives, okay, or you used Samba, or you used Apple to create Apple file share volumes, or used NFS or Linux, you use the distributed file system. All of the EdLab machines actually use a distributed file system, which is NFS. So your home directory is available on any machine regardless of which machine you log into. It's not actually stored on that machine, it's stored on a file server. It's just made available on all the machines you log into. Yeah, so those are the clients, and the server is separate. So every distributed file system will have one, but potentially more than one server. Okay, the server is the machine that is actually going to provide you file system for remote access, and that server will actually have a file server process that's responsible for accessing read, write requests, open requests to the file. Right? You can think of many of these requests as just being RPC calls that go from the clients to the server. When you try to open a file, your client will actually make an open RPC request to the file server, which will then process that and send back data. If you try to read some block of the file, you will make a read RPC call, and so on and so forth. Okay, so there is going to be communication between the client and the server, which could use RPCs. That's a typical way that is used for most of this communication to actually take place. Okay. Now, regardless of whether you use RPC or not, there are actually two different ways by which you can provide access to a remote file on a server, and they are shown in this picture. Okay, so this one is referred to as the remote access model, where you have a client, the file is stored on the server. Every access that the client makes requires it to make RPC request to the server. Okay, so this is called remote access. All the work is done at the server. Okay. The second model is called an upload-download model, where the first time you open the file, the server will send a copy of that entire file to the client. Okay. At that point, the file actually becomes local to the client. All subsequent accesses from that application process is just going to access the local copy. And when the file is closed, then you resend all the changes back to the server. Okay. So you'll see there are trade-offs of the two approaches. In this approach, every I/O request requires a network hop, so it will have higher latency. Okay, it's disk latency plus network latency to go to the server. Okay. In this case, the first time you open the file, you will pay extra overhead of bringing that file over. So there's a larger copy operation if the file is large. But from that point on, all accesses to that file are local. Okay, so there's no network access in this case. Okay, only then when you close the file will you send it back to the server. Yeah, so this is called the upload-download model. Okay, so there are many differences between the two in terms of how cache consistency might work. Here, all the load has to be processed by the server. Here, if there are many clients accessing many different files, each of them will bring a file over, and then all that work is then done locally. Then you upload them, and so on. So there are going to be all of these trade-offs of then you have state versus stateful versus stateless servers, and so on and so forth. Okay? So keep this in mind. These are very simple concepts, but as we get to NFS and many other file systems, you will see how these ideas get instantiated in specific contexts. Yes, question?
So for the upload and download mode,
Yes.
if multiple clients access the same.
Yes, that's a very good question, and we'll come to that. I'll answer that now, but we'll come back to that when we talk about NFS as well. The question is, in the upload-download model, what happens if there are concurrent accesses to the same file? Okay? So if you have an upload-download model and two processes on two different machines open the same file, you shouldn't make two copies and have them make local changes and then have them overwrite each other. That's a problem. Okay, what happens if in that case it degenerates to this model? Okay, the right way is if you have concurrent access, keep the file at the server, have all clients send all their requests to the server, have the server make the writes in whatever operation you want. They should hopefully have used locks and other things, because that's a file that's open by multiple machines is essentially shared data. Right? But that is left to the clients on how they do that. But typically you will not want to do this, where you downloaded the same file in multiple locations and you are writing to them, and then neither client knows about the writes happening at the other. So they will degenerate to this model. Having said that, you should also realize that that is actually considered to be a rare case. Okay? It only happens for certain applications. In most applications, a file is typically opened by one process. So this works in generally, but in that scenario, you have to do extra things to make sure it's consistent. Any other questions here? Okay. There's one typo I just noticed. It says this is stateless and that's stateful. It should actually be somewhat opposite. If you have to keep track of state of which client has actually downloaded what file from you. So you actually have to keep some track of the state. In this case, you can actually be stateless if you want, because all requests are always coming to you. Just process the request and send back the responses. You don't need to know who is sending these requests. Okay, so the stateless and stateful should be flipped. Okay, so depending on which of those two you pick, you will have to decide whether you need to keep track of the state of the client or not. If you have a stateless server, that means essentially there's no information that the server machine has to keep between successive requests from the client. It's completely stateless. You basically process the operation and send back the reply. Okay? And then if you're stateful, then you have to keep track of every file and that is open, which client has opened it for reading or writing. You might have to send consistency messages and so on. And obviously, whenever you maintain state, you have to keep track of, not keep track, you are going to be less resilient to failures because you have to keep track of state of the file. If you crash, then that state goes away. Okay. With that basic concept in mind, let's now do a first case study of an actual file system and understand how these ideas get instantiated. Okay, the first one we are going to talk about is NFS, which stands for Network File System. Okay, so this is actually a very old file system. It has been around for many decades now. Okay, it was designed in the 80s by Sun Microsystem, and in fact, RPCs, the first commercial applications of RPCs was for implementing NFS. This was the first application that was actually deployed, which made widespread use of RPCs. And then RPCs became their own thing, and they made tools available to other users to write their own application. But they actually wrote all the RPC tools to implement NFS back in the old days. So this picture essentially shows you a server machine and a client machine. Okay, so in this case, this is the server machine. We assume that the disk on the server machine stores some files that are accessible on the client. Okay? And the way this is actually implemented using any Unix-like operating system is that you essentially make use of a layer within the kernel, which is called a VFS layer. VFS stands for Virtual File System. Is often referred to as a Virtual File System switch. This is how you can actually plug in multiple file systems into the same operating system. Okay, most general purpose operating systems will have a built-in support for a wide variety of file system. Okay? If you plug in a USB drive, okay, it will basically make that USB drive available to you. Okay? Typically, that might use something like a FAT32 file system, which is a really old file system. Okay? And you can then plug in maybe an NTFS formatted disk, and it will mount that also. Okay? You can have ext3. You can have a whole slew of file systems supported in there. If you have a DVD, it will have its own file system. It's called ISO file system. Okay? So the kernel itself actually has support or code to support a variety of file systems. And the way they are all made to work is using this layer called a virtual file system layer. Okay? Above this layer, users are only exposed to generic or abstract operations such as open a file, read a file, write a file, independent of what type of file system the file is actually stored on. Okay? Each file system would implement its own data structure. It will have a different disk layout and so on. Okay? So when the client application process makes a call, it basically be eventually an IO request, it comes in as a system call. It comes to the VFS layer. The VFS layer has to figure out what type of file system is actually responsible for storing this file, and it will forward that to the implementation of the file system. So under VFS layer, you will have different implementations of the file system. You might have FAT32, UFS, ext3. In this case, you will also see NFS, for example, and so on and so forth. Right? That's just an aside for you to know what a VFS layer is. Now, as far as NFS is concerned, in this case, we only see two file systems underneath. There's a local file system and there's an NFS client. So if you are trying to access a remote file, you will open that file. It will look like a local file to the user. They will not see that this is remote. It just looks like it's on this machine. But when they try to open it, inside the file operating system, it will come to the VFS layer, which will realize this is a remote file. So it will hand that off to the NFS client. NFS client will then construct an RPC request. You'll see that there's an RPC stub, and send that request to the server machine. There's going to be a server process here that's going to receive that request, which will then forward it to the VFS layer saying some client has requested this file. The VFS layer will then actually send it back to the local file system implementation to perform that operation. And then the responses will go back in the opposite direction. Okay, is that clear? So that's basically some high level implementation detail. Just question.
Sorry,
Okay,
what is the system call layer?
what is the system call layer? So system call layer is the interface that the OS is exported to application. That's the OS level interface. That's good for the system calls. Okay, any other questions? So in this case, it's going to implement open, read, write, close. Okay, these are file system calls. Okay, so now here is a long table that shows you all the NFS operations. So these are all the RPC operations that the NFS client will implement for us. Okay? You don't need to go into a lot of them, but there are a couple of things I want to mention. There are two columns here. One says version 3, that's basically version 3 of NFS. The other says version V4, which is version 4 of NFS. The version 4 is the more recent version of NFS. Even now, lots of people still use version 3. Okay? And NFS philosophy has always been keep the server stateless. There should be no state on the server. Okay? That means every time you make the request, all the necessary information to process the request should be embedded in that request. Okay, so server is going to be stateless. After it sends back the response and no knowledge of this client ever accessed this file or anything like that. Okay? That changed, that philosophy which has been held for decades, changed with version 4, where they finally said there are good reasons to actually keep state at the server, and they made the server stateful. And as a result, there are some important changes that were made, which you will see reflected in these calls. So for example, to understand what stateless means, let's look at the open call. Okay? So open is just a way you open a file for reading or writing. Okay? So you will see in version 3, there is no open call at all. Okay? Because what does open do? If you have actually opened a file in Java or any programming language of your choice, when you open a file, you get a file descriptor. Okay? You use that descriptor to access the file subsequently. That file descriptor is a way for you to access state in the OS saying, I am now referring to this file. Okay? So open is a way for the call to tell the OS saying, this process now wishes to access this file, keep some state and give me a descriptor that I can use to subsequently access the file. Okay? So the open actually causes the OS to keep state of which process it is, what file it has opened. But I already said that NFS philosophy has been keep everything state, make it stateless. So the open call is not going to do anything because there is no state that you are allowed to maintain. Okay, the local file system might still keep state, but the NFS client and the servers will not keep state. Okay, that's something you want to keep in mind. Even if the file system is actually stateful, when you layer an NFS on top of that, you are going to have to make it use stateless operation. Okay? NFS is just a layer that sits on top of a regular file system. NFS is not its own file system. It's just a layer that you add to make that file system accessible on another machine. Okay? And you're going to make stateless calls to make all of that work. Yes, question?
So it's really weird that the first create, you can create a regular file in V4. Is that because open does
Yes.
allows?
So yes, so you're asking a good question. So the question is if you look at the create call, which is used to create a file, version 3 will support it, version 4 does not support it. The reason version 4 does not support it is, but the default behavior of any file system is when you open a file that does not exist, it automatically gets created. So in some sense, they're redundant operation. If you have open supported, there's no need to have create. You just open a file that does not exist, and it by default will get created for you. Okay? So now, having said that, there's another call here which is called lookup, which you will see is supported by both versions. So the way you are actually going to check if the file exists, if you have the right privileges to access it, is not through open, but you are going to use a lookup operation. Yes, question.
So you said that the NFS doesn't have maintain the state, but that state might be maintained between the local disk, the physical disk, through the operating system and the process. So is that process just the server, the stub?
Yeah. So the question is, well, I think I will restate what I said. I said that NFS client and NFS server don't, well, let me rephrase. NFS server does not keep state. Client could do whatever it wants. Okay? Server is stateless. Now this stateless server is just a layer that runs on top of a local file system, which could support regular open calls which are stateful, but those are only meant for local access. When you have remote access, you are not going to actually use that mechanism. You have to use other mechanisms that are built into the server to enable that. That's all I meant to say. Okay? The client can do whatever it wants. This is only relevant to the state of the server. Yes. Yeah, that's a good question. What led to the change in philosophy? I'm going to show you many things in NFS version 4 that were not implemented in version 3. Okay? One example is file locking. Okay? Many file systems support locking operations. Locking operation allows you to lock a file so that just the same example that was asked earlier, if two processes access a file, okay, because the file is now shared across processes, to have concurrent access, you need to support locking. Many file systems support locking at the file system level to prevent bad things from happening. Okay? The simplest example where locking is used is email. Okay? If you have a mail client that's opened your inbox that's retrieving mail, and there's a mail server that's delivering mail into your inbox, is a shared file between the client and the mail delivery process. Okay? So it always uses locking, because you might be accessing a mail in your inbox, you may be deleting mail and so on, and new mail gets delivered. So you don't want your inbox to get corrupt. So it uses locking. There are many other examples. When you use databases, you use locking and so on. So all of this is supported by this local file system. And then if you just run a mail server on top of your local OS, everything works. Okay? But if you run this over NFS, it does not work. Okay? Mail should never actually run over NFS, at least now not over NFS version 3, because it doesn't support locking. So you could have file system corruption if there are two processes trying to overwrite one another. So finally, they decided that you have to support all this complex application, which is why they made it stateful. And as a result of making it stateful, they can also implement the upload, download models and optimize network access. We'll see that in a moment. Yes, question? Okay. What's a regular and non-regular file? That's a very subtle thing. So yeah, so regular file just means typical files. You can create all sorts of other files which are directories, symbolic links, all these other things which are actually not real files. Okay, so it's used for those special operations. Yeah, but you don't really need to go into all of this. The purpose of showing you this is to show that there are certain operations which are stateful by definition in a typical local file system. Because NFS version 3 was stateless, you did not have any implementation of that. But when version 4 appeared, it basically had to re-implement those operations. Okay? But with that in mind, let's understand how NFS is actually going to work. Okay? So now, as a client, because you don't know whether the file you're accessing is local or remote, you are not going to change any code that you write. You are still going to open a file for reading or writing, right? Just as if it was a local file. But when you actually do open within your process and you call open system call, and that open system call eventually comes to the NFS client through the virtual file system switch, what that is going to actually do is not send open to the server, is going to actually check if the file exists. Okay, so it's going to do a lookup to say the process wants to open this file. Let me see if it even exists. Does this user have the right permissions to access it, and so on. If it doesn't exist, you don't have permission to access it, you are going to get an error, as you should. Okay? And that's it. You are not going to get a file descriptor or anything like that. If you had actually done open, you would get a file descriptor which you would use for subsequent operation. So you'll see that open has actually just triggered a lookup, and then if that open succeeded, then the next time you actually do a read, you are going to a write. For that matter, you are going to actually send a read or write request to the server. Okay? Now that's version 3. In version 4, you are actually going to do a lookup, and then you are going to do an open that is going to get you a stateful handle back from the server. So you'll see that there's a lookup, there's an open, and then you do a read. Okay? That's one thing. So there is an open. The second thing that you see is that although there are individual RPCs that are going between the client and the server, what NFS version 4 does, it essentially uses a batched RPC model. Okay? You can, it's called a compound RPC. You can batch multiple RPC requests into one packet, okay? And have all of them be performed in sequence and get multiple responses back. That just reduces the interaction between the client and server. It's simply a performance optimization, a compound RPC. Okay? So essentially you are going to use, so that is why you see one request that goes and does multiple things, and then you actually perform those operations and get back responses. So you can have these kinds of additional optimizations in version 4. Yes, question.
So in RPCs, when you add a function, the server stuff would like register that function saying I have it. Is it the same for all the files? So would the server stuff say I have this set of files?
Right. So the question is the server stuff going to say you have a set of files? The way this NFS works is like any other file system. When you open a file, when some particular process opens a file, you're going to send up a lookup request to the server, and then if the file exists, you're going to get a response back. And then if you subsequently try to read or write, you're going to send multiple requests. It's not that the RPC stub has a list of every file that is stored at the server. You're going to send a specific request to the server every time for every process that's opened the file. Okay? Okay. So that's communication. But then I do want to mention an important aspect of NFS. This is true across all versions, which is its mount protocol. Okay? A mount protocol is what is used to make a remote set of files or a remote volume accessible on a server. Okay? And this is typically configured by the system administrator. So here is an example where you have a server machine. Okay? And the server machine has lots of disk space, so it keeps all the home directory and the files within the user's home directory on that server. Okay? And that server directories are made accessible to multiple clients. The way they are made accessible to multiple clients is through operation. The first, the server has to do what is called an export on a directory. Okay? If you export a directory, that means that this directory is accessible on another machine. Okay? It's not as if you just start running an NFS server, all files on that machine now become accessible. Okay? You have to decide which of your files you want to allow other clients to read or write or open. That is done through an export operation. So you essentially have to first export directories. Okay? And then on the clients, you have to run what is called a mount. Mount basically says take this volume on this server and make it accessible locally. And you have to have a mount point which says that I take this entire directory structure and I make it accessible at this part of my local directory tree. So when I have actually gone to /remote and I descend down into this tree, all of these requests become remote access requests that are sent by the client to the server. Okay? So that's essentially called a mount point. It's very similar to how you set up a network drive in Windows, if you've ever done that. You essentially have a path name and then you map it to a C drive, or not C, D drive or a E drive, and so on and so forth. Is this clear? Okay, what a mount protocol is? Okay. So now there are many implications of mount protocol that we have to think of. One is transitive mount. Okay, so here's an example of what we mean by transitive mount. So let's say you have server B that has exported this installed directory that's mounted on server A. Okay? And then server A has actually taken this packages subtree and exported it to the client. Okay? Then the client, the question is when the client actually tries to access the directories within packages, should this set of files, which actually now are stored on a different server, are they available to the client by transitive property? because you made them accessible at this location on this server, and then some subtree that includes that subtree has been exported, should those files be accessible or not. Okay? There are different philosophies for this. So one is to say server B has only shared this with server A. Why should the client get access to server A's files if it, or server B's files? If it wanted those files, it should actually directly mount them here, not go through some other machine, because then you lose track of who has access to your file. Because you make it available to some other machine, that might then export some random files to some other machine, and now some other machine you don't know of has access to your file. So typically transitive mounts are not allowed. You have to basically then remount that volume again here if you want to actually get access to it. You are not going to be able to send a request to A and then have it access the files you are trying to access from B and send back a response. So you are not going to get this form of chaining for security reason. Okay? So now that's actually interesting, that version 3 had this restriction, but version 4 actually supports recursive lookup, because it allows you to do this recursion where you send a request to A and A will send that request to B and so on and so forth, because it allows you to do all this extra work, because it can keep state and do extra security checks and so on and so forth. Okay, so until version 3 this was disallowed for security reason, but version 4 is a different story altogether. Okay. Now the other thing that NFS supports is what is called mount on demand, or what's called auto mounting, where if you actually access a file that is on a NFS bound the first time, it will automatically mount it on demand, and then when you stop accessing it, it will unmount it. So you don't need to have mounted a whole lot of files on the client at all times. Okay. You will see this when you actually log into the EdLab. Okay. If you log in, as soon as you log in, it dynamically mounts your home directory, and when you log out, it unmounts that home directory. Okay. That way, if you have 1,000 users, you don't have 1,000 volumes that are all mounted on the client at all times, which is wasteful resource. Okay. So you can do this mounting and unmounting on demand, which is called auto mounting in the NFS case. Yes, question.
If NFS v3 is entirely stateless, then wouldn't having a ton of open mounts not actually consume any resources besides the fact of the client having to keep track of the fact that it has a ton of mounts?
Okay. Question is, if NFS version 3 is stateless, then if you mount 1,000 volumes, does it have any impact on the server? Because server doesn't need to know or care. It only creates a lot of mounts on the client. In this case, we are actually trying to store client resources, not server resources, because you would have to have those n mounts on the client that are accessing, not accessing, but have mapped onto volume, and they just consume resources on the client. Server is not an issue with auto mounts. It's we are trying to optimize the client for auto mounting. Okay. Okay. So NFS as a specification is designed to be really general, so that you can use it for any kind of local file system and make it accessible over NFS. Okay. And the original spec says that the underlying file system needs to only support 4 operations for you to be able to run NFS on top of that. And you will see that it's the type of the file, the size of the file, some change indicator, and some file system ID, which is a very basic minimal set of attributes that the local file system has to support for it to work with NFS. And they made this design decision to allow NFS to work over a wide variety of file systems. So your file system doesn't even need to have the concept of the owner of a file or a user of a file, because there are some file systems that don't. Okay. Specifically, if you have FAT32 file systems or DOS Windows file systems that are old, they did not have a concept of owner. Okay. And USB drives, when you share it, you know that it doesn't actually have owner. You just create a file, it's there on the file system. And even that is will work over NFS, because it has a very small number of mandatory attributes. Having said that, there are a whole slew of other attributes which, if the local file system supports, makes the job of NFS much easier. Specifically, you can have access control, you can have owner of a file, last modified times, and so on, which are standard things you expect of a file system. Okay? But they are not mandatory for NFS to work. It will work even without that. Yes, question. Can you repeat your question? How? Okay. The question is, how do you handle duplicates when you might have some files on your local file system, the same files exist on the server. If you mount it, you will have 2 versions of them. So, NFS is not going to handle that for you. Okay. You will just have essentially 2 ways to access that duplicated file, one by accessing the local copy, one that accesses the remote copy. They will have different path names. You got to remember that. They won't be, because you mount at a particular point. So, typically you will mount something in /mount/machine. So, they will have different path names. Okay. So, you can actually distinguish between them as a user. Okay. So, now let us get into issues of sharing and caching and things of this sort. So, the important difference between NFS and local file system is NFS implements much weaker consistency semantics than a typical local file system. Okay. In a local file system, you can open a file, write to it, hit save, and then if you open that same file in another process, you will see the saved content. That is the expected behavior. If you change the file and then you open the file again, you expect the changes to show up immediately. Okay. That is not true in NFS. Okay. And you can even try this experiment. You can log into 2 machines, and then you open a file in one machine, you write something to it, you hit save, okay, and then you actually, if you open that file in another machine, it may take up to 30 seconds for those changes to be visible. The reason for this is NFS implements caching, and it uses a very weak form of caching. When you actually write to that file, it only saves it to the local cache. It hasn't even sent it to the server. Every 30 seconds, it will start flushing this data to the server. So, the server is going to know about your write and save potentially 30 seconds after you actually hit save. Right. If you had strong consistency, somewhat like what you are implementing in lab 3, whenever you write, you actually do write through caching. You actually go and change your database or change the file itself. NFS implements what is called write back caching. It only writes to the cache and returns, and then later on the cache is flushed to the server. Okay. This is done for performance reasons, because most of the time, if you are the only client who is accessing this file, why bother? That is the philosophy. You can just flush it at a later time. All your reads and writes are local to the cache. Okay. They are finished much faster, but you are going to get consistency problem, and that is what is actually shown here, where in a local file, if you have file which are, let us say, 2 characters A and B, process A opens that file and writes C and hits save, and then if another editor opens that file, you will see ABC in this case. That is not the case here, because you have caching. So, you have file AB, it is cached at the client, and then when process A writes C, it is actually kept in the cache, and 30 seconds later it is going to be flushed here. In the meantime, if you open that file, you still get the old copy from the server in your cache. Okay. So, you will essentially have this weaker consistency semantics that can cause difference from what you actually expect in a local file system. Okay. So, typical approaches are, once you write to a file, if you want the changes to be sent to the server immediately, you have to call something called flush, okay, or sync, which will essentially take all of that dirty pages and send it off to the server. If you leave it to the OS or leave it to the NFS client, it will essentially take up to 30 seconds. This is how most implementations actually work. Okay. So, weak form of consistency, something to keep in mind. Okay. We will see many file systems that do all similar stuff. They say consistency is expensive, less optimized for performance. Consistency can be handled by the user or user applications. We will not worry about it at the file system level. That is the typical philosophy. Okay. Now, there are other file systems that try to do better, and depending on what kinds of consistency they implement, you are going to get what are called different file system semantics. Okay. The standard local semantics are also called Unix semantics, where changes to a file are immediately visible to other processes. So, you make any change, any other process that opens that file immediately sees that change. That is called Unix semantics. Okay. Session semantics essentially says that all changes are only visible when the file's IO session finishes. When you close the file is when you are going to flush everything. Okay. That is even longer delay than what NFS will do. NFS will flush everything every 30 seconds. But session semantics says from the time you open to the time you close, all changes can be kept locally. Only then do you actually flush everything to the server. Okay. So, that is essentially session semantics. Okay. We will see file systems that implement transactional semantics, which means not only is it going to be visible, they will get atomic guarantees where you can roll back changes and things of that sort. Okay. They are useful when you're implementing databases or remote operations and things of that sort. Okay. And then there are other file systems that basically have what are called immutable files, where once you create a file, you cannot actually change it. If you change the file, you create a new version of the file. So files are versioned. Okay. Every change creates a new version, so you can actually go back and look at old versions and things of this sort. Okay. In Mac, you have things like time machine that keep versioned files, okay, because every time you make a change, it creates a new copy, or not really a real copy, it's a virtual copy, but you can actually have all these versions sitting there. So that those are implemented in some file systems as immutable files. Okay. Files don't actually change. Okay. If you change them, you create a new immutable copy. Okay. There are different design decisions used in different file systems. Yes.
Does NFS support horizontal partitioning if you have a lot of data?
Oh, can you repeat your question? NFS what?
Support horizontal partitioning. I mean, like you partition private data on one server.
Yeah. Okay. So the question is, does NFS support horizontal partitioning? So NFS by itself does not actually do any partitioning at all. Okay. It expects the system administrator to do whatever they want to store their files across multiple disks, multiple volumes, and then mount those volumes on the right machines. Okay. In that sense, it's a very primitive file system. It's not a distributed file system. It's actually a networked file system. You are just making a local disk accessible on another machine. A true distributed file system will do what you are saying, and we are going to look at distributed file system next time. Because this is the most rudimentary form of remote access, but not necessarily distributed. You are not going to take a file or file system, spread it across multiple machines for load balancing and so on. But next time we will actually see such file system. Okay. So now let's talk about file system locking, which is the whole reason version 4 actually became stateful. Okay. Because until version 3, this file server was stateless, so it couldn't implement locks. Okay. You have to realize that locks actually are stateful objects. A lock can either be free or in use, so you got to track, if you create a lock, what the state of the lock is. Okay. If you want to implement file system locking, therefore you have to make the file system or the server stateful, and you cannot do locking in stateless servers. But because version 4 allows you to keep state, now you can implement full locking as you would normally do for the local file system. Yes, question.
I guess I don't quite understand the distinction with stateful and stateless in here, because you are writing to persistent backing storage, right?
Yes.
So you could theoretically implement a lock as just something that's on the file. When you try to read it, you can't read it because you look at the same thing first.
Okay. So the question is, what does state mean? Okay, and then could you not, because by definition disks keep data, and that data is state. So you are saying what does difference between stateful and stateless mean? So when we say file server state, we mean memory state. Okay. Indeed, all file systems are persistent, and persistent objects by definition are state, but we are not talking about what you store on disk. We are saying, can you actually keep track of some state information in memory? Okay. So lock is an in-memory object, it's not a disk object that you keep track of, is the lock in use on this object and things of that sort. Okay. The other state you maintain is which clients are opened what files for I/O access. That's also state. And typically in a local file system, that state is kept inside the OS. The file system keeps track of that. That's in-memory state. In NFS, you don't do that. Okay. That's what we mean by state. Now, as to your other question, could you implement a lock by creating a lock file on disk? Perhaps you could. There are many applications that create a special file .lock to indicate that that's a lock on the file. Okay. But you have to actually make sure that access to that file is atomic. Otherwise, you are not going to get true locking. That's just poor man's locking in some sense. Okay. So to get true locking, you actually have to implement a real lock. Any other questions? Yes.
So in order to use NFS locking, does the application that's say like opening files or whatever need to be aware that it's running on top of NFS, or could like it use like some sort of like system command to say I want to lock this file.
Right. Okay. Okay, that's a good question. The question is, if you want to use file locking in your application, does your process need to know whether it's actually running on top of NFS or could you use abstract operation? Typically, the general philosophy in any OS is when you're writing your application code, you don't care about what file system it runs on. Right? When you call open or read write in Java or C, C++, Python, you have no idea what underlying file system does. Right? And that's the way it should be. You shouldn't have to know. Okay? Now, having said that, if your program or your programming language supports file locking, okay? So you basically call file.lock and then try to lock a file. If that file was actually stored on top of NFS, you would get an error because your NFS client would say can't do it. Okay, so you would then basically get an error in application. However, if you had done version 4, that will actually succeed. But if you had actually the same file was stored on your local file system, that same process would call that same function and that would succeed because the underlying file system does support locking. Okay. So you'll just see different behavior, although you don't need to know whether it's running on NFS or not. That's the way you should think about it. Okay. So here you will see that there are interesting things you could do. You don't just need to lock a file. You can lock some byte range of a file. So you can say lock bytes 10 to 100. Okay, only those bytes of the file are locked. Other bytes could be actually used. So you can lock the whole file. You can lock a range of bytes and so on. All of this is interesting if you are actually implementing databases. Okay. In databases, you could put a lock on a table. You could put a lock on a record. A record is simply a range of bytes within a file. So you can say, I just want to lock that record when I'm changing it. So you can do those kinds of things using file level locking. Okay, so it is actually interesting that file locking is far more fine grained than just lock the entire file. You can lock parts of the file if you want, and then you can have multiple locks on different parts of the files as well. Okay, so now the next thing that I just want to mention is another way to think about locking, which is called share reservations. Yeah, so reservations essentially say that what kind of operation do you want to create locks on, and then when some other client tries to access a file in a particular mode, should it be allowed or disallowed. So think of them as read-write locks in some sense. Okay? I presume all of you know what a read-write lock is. Right? So there's sort of a generalization of lock, where in a lock there can be only one entity accessing an object at any time. In a read-write lock, you can have multiple readers but only one writer. That's the definition of a read-write lock. And you will see that if you essentially have a write lock and then somebody else tries to, well, I guess you have a write lock, the column is what you want to do. Then if somebody else tries to do a conflicting operation, it is essentially going to fail. So this table is simply showing you that NFS actually implements this notion of read-write locks through a concept called reservation. You can reserve a file for reading, you can reserve a file for writing, which means that you actually have a lock on that operation and other operations are going to fail. Okay? So you can have concurrent readers, but only single writers. That's the way you want to keep this in mind. Again, this requires you to keep state inside the file system. Okay? So that's something you want to keep in mind as well. Okay? So I won't spend too much time on this because I do want to spend a little bit of time talking about caching and other things. So I mentioned some time ago that NFS has a very loose form of consistency. The reason this is the case is if you actually read the NFS spec is a standard. So anyone can write an NFS client or an NFS server. So long as it conforms to the spec, the client and server can interoperate. You can run a client on Windows using one implementation. It can access an NFS server that's running on Linux. It doesn't have to be homogeneous because both of them use the same interface. They're all interoperable. That's the way you should expect any remote distributed application to work, and NFS does that also. Now in this spec, if you read the spec, you will see that there is no mention of caching at all. Okay? It just says here are the 20 operations, and I showed you that table. So it says here are the 20 operations that you need to support, and then you essentially have a compliant implementation of a client or a server. No mention of caching. All caching details are left to the implementation. So you can decide if you want to have caching at all. If you implement caching, what cache consistency to use is also left to the designer. Okay. So most designers essentially said, if there is no need for caching, we'll implement caching as a performance optimization, but it doesn't actually require you to implement any specific consistency semantics. So let's just do something that is weak. Okay. We will basically keep a cache, as you see here. Okay. So now you will see that there is an NFS that's a server. This is the client as a client application. So whenever you are trying to access your data, you are going to go to the NFS client code in the VFS switch, and it's going to first look in an in-memory cache. Is this data already in the cache? Did I fetch it previously from the server? If so, you are going to return. If not, you are going to actually send, there's going to be a cache miss, you are going to send that to the server. Okay. Similarly, when you write, you just write to the local cache, and then you will flush it at some later point in time. Okay. So there is no requirement that you even flush every 30 seconds. That is what many default implementations do. You can pick whatever you want because there's no requirement for caching at all. So you can write your own client that flushes every 20 seconds. That'll still be fine. Okay. But by default, you will see that a lot of Linux implementations or Unix implementations have chosen 30 seconds as an interval. Why 30 seconds? We don't know. Okay, but that's what is used. Okay, you could have picked 50 seconds or 10 seconds, doesn't matter, but it is what is actually used, which means that there's always going to be up to 30-second delay for any changes made at the client to become visible at the server. Okay. Now, because version 4 is stateful, it actually does some interesting stuff that is not possible in version 3. Okay, you have to realize that everything until version 3 was a remote access model. Every client operation was sent as an RPC request to the server, performed as a server, and you send the results back. Okay. Because version 4 is stateful, you can implement the upload-download model that I talked about as well, which is essentially what is shown here. Okay, client asks for the file. Okay, you open the file or you do a lookup on the file. If this is the only client that's accessing the file in the system, then the server is going to say, here, take a copy of the file. Okay, the file gets delegated to the client. The client becomes a temporary server for the file. All subsequent file operations are now local because you own the master copy of the file in the system. Okay. The server is actually going to track. It's going to keep state that I delegated this file to this client. The master copy is actually at the client, not at the server. So the copy at the server is out of date. That much it tracks. Okay. If another process opens that file for reading or writing at the same time, you can recall the delegation saying send the copy back because I am going to go back to my upload download to my remote access model because there are concurrent accesses to the file. Okay. If you are single reader or writer, you can do delegation. If you have concurrent accesses, you can actually recall any delegation if you have made and then go back to the old model where all requests are sent to the server for processing. Okay. Yes, question. Okay, that's a good question. How does it handle failure? So typically, this is not that resilient to failures. So if you actually fail when you're delegated files, then you will actually lose some changes. That's one problem because all state is kept in memory. So, yes, so I think all of these are configurable parameters. So you can say, don't do delegation or do.
But you can only do that as the administrator. You can't do it on a per file.
Yes, on a per file basis, you don't know what is happening. So you will basically have all of these optimizations taking place. This is strictly better than caching because you actually have the copy of the file. You don't have a cached copy which is still being sent to the server. You own the master copy. All changes are actually local to the file. Okay? But yes, I think as an individual user, you cannot dictate what NFS should do, but you can certainly do that as an administrator. Okay. So the important thing is in version 4, you have both. Okay, you can essentially send all accesses to the server for processing, or you can bring a copy over, okay, and then all changes are not changes, but I/O is local, which gives you performance gain because all the network delays in sending all the making RPC operations are all gone. Okay, so everything is local to the client. Here is another issue that you have to think about, which is RPC failures, okay, because as I said, NFS runs over RPCs. Okay. What happens when you make a RPC request? Let's say you try to read or write. Okay. The RPC request fails. Maybe it is lost over a network, as you might see. You might send a request, you didn't hear back. Okay. You can read. So what NFS will do is it will take a request, when it's made an RPC request, it will keep a timer. If you don't get a response from the server within the timeout interval, it will retransmit the request. Okay, so you will see that there's a request number, okay, 1, 2, 3, 4. If there's a timeout, it will retransmit the request. However, you have to keep in mind that whenever you retransmit RPC request, this has to be idempotent. Okay? If your request was append character A to the file, you send that request. Server processed the request, but the response got lost, okay, which is what we have seen when we had RPC failure. So the client is going to time out and send the same request again, append A to the file. If you reprocess that request, you have now processed it twice. Okay, it's going to give you incorrect results. So even though you are doing using timeouts and retransmitting requests, from the server's perspective, every operation has to be idempotent, which means that regardless of how many times you send it, you will get the result as if you processed it only once. Okay. So how do you do that? Okay, the way you are going to implement this in NFS is through essentially a request cache. Okay, it's called a duplicate request cache, not a typical cache. So every operation that has been performed by the server, you will keep track of it and you will log it, saying I received request number 1, 2, 3, 4. I successfully executed it and produced this response. Okay. So you will keep all of that in a special memory cache. And if you actually get a request from this client, okay, first you always check in the cache, have I seen this request before? If you've seen the request before and you already processed it, you are not going to send back, reprocess it. You are just simply going to take the response that is cached and send back the response. Okay. Very simple idea to get idempotence. You could have done something a lot more complicated. Here you just keep track of every request I have processed recently. Whenever a new request comes, you say, did I process it already, or this is a duplicate request because of some timeout or some network packet losses. If it's a duplicate request, then you are going to just look in the cache saying what was the response because you processed it. Just send the reply back. Don't process it again. If not, then you actually process the request. Okay? So this is going to give you idempotency without doing anything more complicated than just keeping a duplicate request cache. Okay? So that is what is essentially used in NFS to deal with RPC failures. Now NFS by default doesn't actually dictate whether you have to run it over UDP or TCP. If you are running the RPC or UDP, you are going to have all these problems. If you just run this over TCP, you don't need to worry about this because TCP is taking care of retransmissions. Okay? You don't actually have to deal with it at the NFS layer at all because if the packet gets lost, TCP retransmits that packet for you. It's not going to be received twice by the server because TCP gives you reliable delivery using retransmission. So you get every packet only once from the network. You're not going to get the packet twice even though it's retransmitted. So this only, it's relevant if you are running NFS or UDP. Then you might actually have retransmission and so on. Clear? Any questions here? Okay. So the last thing I want to say is NFS and security, okay, which is important whenever you are trying to access any files over a network. Okay. Again, until version 3, there wasn't a whole lot of security built into NFS. All RPC requests are going over clear text. Okay. So if you actually start sniffing network packets, if you are reading a file, you can actually see the contents of the file going over the network. Okay. Which is obviously not good because if you are trying to read a sensitive file, then it's all going over the network unencrypted. Okay. So clearly you don't want that to happen. So now they do have security built in, and the security is essentially going to use encryption over the network. So all your reads and writes are going to be encrypted. So you essentially have your RPC stub and at both ends using a secure channel. You can essentially use SSL to encrypt your communication. You use secure sockets and run everything over secure sockets. Okay, this is important in any distributed file system because even though the files may be kept on a secure machine, the network transmission of reads and writes is insecure. All your file contents are going in the clear over a network. You don't want that to happen, so you want to use encryption to do that. The most standard way is encrypt your network connections using things like SSL, which give you encryption using socket abstraction out of the box. Okay. There are many other things that NFS will do, which are things like Kerberos and things of that sort. Okay, NFS doesn't actually dictate what encryption you use. It can actually use pluggable encryption, saying you like to use a certain type of encryption, you can plug it in and your RPCs will run over that kind of encryption. Okay, so it doesn't actually require that you use a certain type, but it supports a variety. Okay. It's always a good idea to do this. Okay. Having said this, on a LAN setting, most NFS traffic is still going unencrypted. Okay. Almost certainly all your NFS files in EdLab not encrypted between the client and the server. But in general, you want to do that because you have security implications if you don't do this. Okay, especially if you're doing this over wide area where you mounted a file over the internet, you don't want all your traffic to go unencrypted. Okay. So NFS actually implements all of this using what is called secure RPCs, which is RPCs that run over SSL. Okay. Any other questions here? Security. Okay. So a little early, so I'm going to still end it here because we are done with NFS. So next time we are actually going to look at more complicated distributed file systems. Okay, we'll look at how you can partition your files across multiple disks, store them on multiple servers, give larger file system abstractions, and so on and so forth. Okay. So let's stop here for today.